Hello everyone, welcoming you once again, and I hope your board exams are going fine. Both CBSE and ICSE, and ISC and CBSE Class 12 are also on the way. So I hope you are giving a great exam. And the next big rock for the ICSE is physics. So with the topic which is from electromagnetism, which includes Lenz and Faraday's law. So initially, let's start with the laws only word to word, though you'll get the same thing in your book as well. But still, I'm just reading it out. Wherever magnetic flux linked with the circuit changes, induced EMF is produced. Okay, so whenever the magnetic flux linked with a circuit changes, induced EMF is produced. That is the first law of Faraday. And the second law of Faraday states that the magnitude of induced EMF is directly proportional to the time rate of change in magnetic flux linked with the circuit. Now comes the last one, that is the Lenz law, that states induced current produced in a circuit due to the change in magnetic flux is also, like always, flows in such a direction that it opposes the cause that produces it. I hope like my handwriting is mashallah, but disclaimer for that. So, but these laws you will get in your book as well, right? But the explanation behind it, that is the most crucial thing. So I'll now get into that. Okay. Okay. So we'll come to the Lenz later. We'll commence with Faraday. Now, according to Faraday's law, see, here is a magnet, electromagnet, right? Now, as we know that the magnetic field lines always run from north to south, right? So these are the field lines, emerging from this electromagnet. And here is a circuit. Here is the circuit. Now, according to Faraday's law, that there has to be a change. There has to be a change in the magnetic flux. Now, what is magnetic flux? Magnetic flux is nothing but the number of magnetic field lines passing per unit area. So you have to either increase the magnetic flux, that is the number of magnetic lines linked with this circuit. Here area means the area, so the area of this, the cross-sectional area of this circuit I'll consider, right? So when the number of field lines passing or crossing through the circuit is increasing or decreasing, there will be an EMF induced. There will be EMF induced, right? So I can't keep it stationary, right? If I keep this circuit and this magnet both stationary, then definitely the number of field lines passing through the area will remain same constant. So under such condition or under such circumstances, there won't be any EMF produced. Is that clear? Now I have to increase. Now how can I increase? There are like 2 to 3 ways that I can either increase or decrease, right? Let's talk about how can I increase it. If I want to increase it, I can drag this circuit closer, because instead of here, if I drag it closer, see, more field lines now passing through it, right? And if I drag it away, now see, number of field lines here passing 1, 2, 3. Here in the initial stage it was 1, 2, 3, 4, 5, 6, 7. Here it is 1, 2, 3, 4, 5, 6, 7, 8, right? So number of field lines passing through this circuit, which is flux, the magnetic flux is increasing when I am bringing the circuit closer to this north pole, right? And when I am dragging it away, right? When I am dragging it away from this electromagnet, then the number of field lines or the flux linked with the circuit is decreasing, right? Is that clear? I repeat once again, that is whenever the number of field lines passing through per unit area, commonly we call it flux, linked with the circuit increases or decreases, there will be an induced EMF. Now, we have to either increase or decrease. Now this, why should I increase, why should I decrease, and how will it impact? So Lenz will come into play, that is later, but now as of now we are dealing with Faraday. So if I am taking it away from this electromagnet, so number of field lines that is linked, the flux linked with the circuit is decreasing, and when I am bringing it closer to the electromagnet, in that case the number of field lines crossing through the circuit is increasing. So in turns the flux is increasing, right? This is one way. Another way is I can bring this electromagnet closer to the circuit, keeping this circuit as stationary. If I bring it closer, so obviously again the number of magnetic field lines or the flux will increase, and if I keep it away, like if I take it away or make a distance, take it farther, so in that case the number of field lines passing through the circuit will decrease, right? There are two ways. And another third way is if I turn the circuit, like it is you like imagine as a circle, right? Now if I drag it, now it's a three-dimensional figure, it's a bit difficult for me to explain, but I'm still trying. If this circle is like, you know, rotating or shifting, in that case what is happening? Less surface area is coming in contact with this magnetic field lines, right? Is that clear? Okay, is that clear? Okay, I'm trying in a bit another way. I don't know how far I'll be able to with this. I'm trying to explain. Let's assume it as a circle. Now the magnetic field line, suppose passing through here, if in this way, if I keep it like this, so number of field lines passing through this will be more, right? Number of field lines passing through this circuit will be more. I'm sorry, I had an operation, I can't lift my left hand, so that's again a difficulty, but considering your exam, I have to do this. Now if I rotate it like this, now the number of magnetic field lines crossing through this or passing through or touching through this circle is getting lesser, because see, less surface area is there. From your point of view, if you keep it like this, you are getting more surface area. I'm still trying. More surface area you are getting here, but if I turn it like this, so see, less surface area you are getting, so number of magnetic field lines or the flux linked with the circuit is getting lesser in this position, and in this position it is more. So if I keep on rotating this, so alternatively what will I see? I'll see, you know, periodically there will be an increase and as well as decrease in the magnetic flux. So as well the induced EMF will be impacted, but in the EMF will be induced, that's for sure. Okay, that is the Faraday's first law. And Faraday's second law, what did it state? If you remember, what is the second law of Faraday? I read it out, right? It is also there in your book. It states that the magnitude of induced EMF is directly proportional, right? It's directly proportional to the time rate of change in magnetic flux linked with the circuit. So what does this indicate? It indicates that, you know, the faster you change the flux linked with the circuit, the faster you change, like the faster you drag it closer or away, take it away, more EMF will be produced. Okay, it is like you have to make it fast. This shifting or this rotation or shifting of this electromagnet, the way you can change the number of field lines, the flux crossing through this circuit, the faster you can change, the faster you can develop, you know, EMF in the circuit. So that is the second law, right? So up to here it is clear. It is still now. I've just said about Faraday. Next I'll come to Lenz. Now according to Lenz's law, what Lenz said that the induced current produced in a circuit due to the change in, you know, magnetic flux always flows in such a direction that it opposes the cause that produces it. So basically what it's stating is that it opposes its own cause of production, right? Now as you can see here, if, like as I said first, that you can't keep it stationary, you have to move it in either way, right? Now if I drag it away, if I take it away from the circuit, then what will happen? See, the current will generate, or the EMF will generate in this way in this circuit. So that is a what? Clockwise. See, if it is like this, from your point of view it is like this, so it is clockwise, right? And clockwise means what? South pole. I explained it earlier in a video, in a electromagnetic, in which I explained the Snow law and all. So the south pole will be produced. Now when I'm taking it away from the circuit, south pole is produced. When I'm taking the north pole away, try to understand what I'm saying. So opposite pole is produced. Now it will drag. Now it will drag, right? But as soon as it's dragged, the problem is that, you know, again the reverse phenomena will take place. What is that? I'm explaining it now. Now if I like like take it towards the circuit, what will happen? Earlier I took it away from the circuit. This arrow, remember this arrow, it has been taken away from the circuit. So opposite pole was produced. Opposite pole means there will be attraction. So south pole will attract the north pole. So there is an attraction, right? Now once it is attracted and it is dragged through the circuit, then the reverse phenomena will happen. What will happen? Then instead of clockwise, as earlier we have seen that there will be a clockwise EMF produced. Here anti-clockwise EMF will be produced. That means this arrow will change. This arrow will change. This arrow will be now like this. That means what? There will be anti-clockwise rotation. That means north pole will be produced. Now here north pole will be produced and here south pole will be produced. So now north and north will do what? They will repel each other, right? There will be repulsion. So in that case, this north pole of this magnet will be, repelled. So it will go away. And again it will go away. Sorry, I removed. Sorry. Okay. Sorry. So when it was taken towards, like when it was attracted by the circuit, what happened? That, once again, the anti-clockwise rotation, so north pole was produced. So again, due to the same pole, there will be repulsion. Now due to this repulsion, now it will be repelled away from the circuit. And once again, then what will happen? It will be south pole. It will be north pole. And these arrows will change, right? These arrows will once again be clockwise. So what you have seen? That when it is going away, it is producing the opposite pole and it is pulling it towards itself. And when they come closer, then anti-clockwise cycle is produced. So north pole is produced. So two similar poles again will repel each other. So once it is like repelling and then it's attracting, there is a repulsion attraction. There is a continuous and a cyclic process of attraction and repulsion going on, right? And there is a spontaneous change and a cyclic change in this cycle, in the direction of this cycle. So once it is clockwise, again it is anti-clockwise. And similarly, suppose if I change the poles, like instead of south, if I put here north, and instead of north, if I put here south, again what will happen? When it is taken away from this, opposite pole will produce. That means here it will be north. And this will be south. And when it is again repelled, once again what will happen? There will be opposite pole. As you can see, here is south, where it is north, and again it will be dragged, and again there will be same poles produced. Here it will be south, it will be north, right? So the change is happening according to the Lenz law, and here you can see that north and south pole, right? I have changed it now. Earlier it was south, here north. So when I am changing this phenomena is also changed. So in the simplest way, that is according to Lenz law, once it comes closer, same pole is produced, then it is repelled, and when it goes away, then opposite pole is produced, and then again due to the attraction it is pulled towards the circuit, and again the opposite pole produced, and then it is repelled away. So in this way, it's a continuous process that keeps on going, and in this way the EMF keeps on producing. So that is the fundamental thing about Lenz and Faraday. So the main thing is you can't keep it stationary. You have to either increase or decrease. So in order to do so, you have to you can do either of the three in a process. Either you have to take this magnet towards the circuit or take it away from the circuit. You can take this circuit closer to this magnet or take it away. And last but not the least, you can rotate it. You can rotate it as I just demonstrated it earlier. So in that way, you can continuously change the magnetic flux linked with the circuit, and in turn it will generate the EMF. Now if I come to the formula, that is E equal to minus, actually E proportional to df by dt. Now this is very easily understandable. Why it is minus? Because if this phi is increasing, please try to understand this is the conceptual thing. This phi d phi dt is, so this dt is this time, dt denotes the time with respect to time. If this phi is increasing, right, if the phi is increasing, this EMF will be reduced. EMF will be reduced. So since the EMF is reducing, that's why this minus sign has been assigned here. Getting my point? So that is the thing, because when it is coming closer to it, so phi increases. So once phi increases, it again repels. So whenever this number of field lines or the flux linked to the circuit increases, it is repelled. So due to the repulsion, this minus sign is there, because then the current and the EMF produced drops down. Getting my point? So this is one thing. And if I put, since you know that this is a sign of proportionality, if I remove it, I have to bring a constant. This constant is K or N, you can also do, but in SI system, not CGS, in SI, K can be considered as 1. So if K is 1, then it is forming, it is coming out to be d phi dt. Got it? I hope it's clear, right? Let's hope it's clear. It should be. Now, a conceptual question is coming here. This arrow indicates the current. Current is increasing. There are three cases. I'm coming one by one. The current is increasing. If the current is increasing and this is the circuit, now you have to give this question is based on the direction of the circuit, right? So in which direction the EMF or the current will flow? See, I is increasing. I told you the formula is E equal to minus K d phi dt, right? So there is a minus sign, and I said that if d phi, that flux linked to the circuit with respect to time, is increasing, that means EMF due to this minus sign, as I told you why minus sign has been assigned here, so E, that is EMF of the current, will decrease in the circuit, right? So they will be in mutually opposite direction. So if it is, the current is flowing like this, this will be the direction of the induced EMF, right? Now if I reverse this arrow, then these arrows will also be reversed. As you can see here, it is in clockwise motion. Since it is like flowing from left to right, it is, and I is increasing. Make sure I is increasing. Had the I been decreasing, then it would have been, anti-clockwise. This arrow would have been in anti-clockwise, right? Since I is increasing, then definitely the flux or the EMF generated will decrease. So they will be in mutually opposite direction. See, it is going in this direction, it is going in this direction. So it is, in mutually opposite direction. Now here in the second case, I is decreasing. I is going upwards direction, and here it was increasing, it is decreasing. I is decreasing. So in that case, what will happen? They will be in the same direction. Like it will rotate like this, and it will also rotate like this. Okay, since I is decreasing, so they will be in the same direction with the I, because I is decreasing means what? The d phi is increasing, so they will be in the same direction. And in the third case, the current is steady, and as I told you, if there is a steady current, that means both the conductor and the circuit are stationary, right? So under such circumstances, no current will flow. So there will be zero current. You can write here 0. So zero current will flow through it. Got it? So now if I reverse this arrow, this will also reverse. Instead of I is decreasing, if I make it increasing, then these arrows will be reversed. And instead of I, direction of I, even if I just alter or change it, if I like, instead of upwards arrow, if I put a downwards arrow, then also it will change, right? Because I is decreasing, but going downwards. So in that case, they will be in this direction. And it will be in this direction. Right? Getting my point? So it's all about the direction of the current and whether the current is increasing or decreasing. So keeping in mind, you have to do or you have to answer the questions. And as we know that, physics paper, at least in recent years, it is coming really conceptual. So don't take risk, and whatever question that strikes your mind, just feel free to ask me. Those, I'm not only asking it to my direct students, but those who are, my viewers. If you have any doubt, you can ask me on the eve of exam, because you all are my student on the eve of exam. Since the board is knocking at the door, physics is knocking at the board has already commenced. Physics is knocking at the door. And it's a big rock, I must say, among all the science papers, because physics is giving really, really trouble for the last few years, in recent years. So be prepared. Okay, is that clear? I hope so. Okay, another interesting question. A magnet has been brought and it is passed through this coil, right? Through this coil, it is passed, and as you can see the arrow. Now, according to the EMF produced, which graph represents it the best? You can take it as an MCQ question. There are 4 graphs given. So again, while approaching this, first I have to start with the formula, that is equal to minus K d phi dt. Now, when it is coming closer to the coil, please try to understand, when it is coming closer to the coil, what will happen? The EMF produced will increase or decrease. The magnetic field lines, it will experience a strong repulsion, right? Because obviously same pole will be produced and it will create a repulsion, but ignoring that, it is being taken and it is being passed through this coil and taken away. So once it is passed and then taken away to the right hand side, then gradually the EMF will increase, right? Initially it will decrease and then it will increase. Now you can solve it. See, it is starting from here, coming to this point and then increasing. There is no negativity. Like there has to be something negative, because it is decreasing initially when it is entering and crossing through the coil. Now, here also it is starting from 0. So there is no point of 0, because once it is in mobile state, obviously the current or the EMF cannot be 0. In this case, it is decreasing, fine, but once it leaves the coil, it has to increase, but there is no exponential increase in it. Here, that is the only feasible case, because when it is entering, it is coming closer to the coil. See, the EMF is decreased, and then the EMF is decreased, and once it is taken away, while it is in the middle, it will be 0, right? There will be no EMF right at the middle, and after it is taken away from the coil or the circuit, then it is increasing, because once it is going away, then again what will happen? That the positive EMF will produce. So your option is B. Got it? Clear? Thank you.